I'm starting the stream. Hello everyone. This is going to be a little bit of chill maths live on Twitch. I'm thinking about prime numbers again. Maths2222 is in chat. Am I Maths2222? You've done something with Desmos again. You've made the Rubik's Cube better. Let's have a look at that. Last time on the show, you were showing me this. Oh, okay. You've now got action buttons over here. Yeah, that's nice. That's very good. Okay, cool. Oh, and this is fun because now I can reset it, and this will be the Rubik's Cube of my dreams, where I can mess around with it, but also reset it. So it spins the side. So I want to spin the yellow side. Yeah, nice. Okay, good. But if I screw up, then I can. Yeah, this is good for like trying to invent my own algorithms or something, where I can spin the same sides again and again and again and work out what the order of that operation is. Good stuff, like it, but then reset when I get confused, which is one of the learning barriers for me with playing with an actual Rubik's Cube. So you try something out and if it doesn't work, then it's quite hard to start again. Oh, I see. So it's running a thing it's constantly running something. And you can also, this has now got, it's now got the 3D rotation thing going on with the cube like that. Very nice. So you can have a look at it from different angles. Very good work, Maths2222 in chat. Excellent stuff. If everybody else wants this Desmos thing, the link is, I guess, on screen or also in Twitch chat. Very nice. I like that a lot. The perspective is kind of cool. Is it doing what's your 3D model? Maybe let's not do too much of this, but it's doing something, isn't it, with perspective maybe? Am I imagining that? No, you do have perspective. Look, these lines are going off to a vanishing point. It's not just 3D points projected onto a 2D plane. There's some said stuff going on, isn't there? Hi Mary, hey Rice Cooker Man, hi everyone who's in chat. This is really good. Well done, Maths2222. Oh, in the 3D functions folder. Yeah, but I like Desmos code. No, did you build this? Is this a Desmos thing or is this a U thing? Anyway, increase window size. I find Desmos stuff really hard to read because all of your variables have to have these subscripts on. I find that tricky. Also, I have no chance of understanding what's going on here, right? Yeah, no idea. That's a U thing, okay. Yeah, no, I have just no chance, right, of having any idea what you're doing. It's just one of those things. Oh, look, projection. But wait, what? This is storing an vector. Yes, this is normalizing a vector. So somewhere in here, whenever I say U, I have to remember that means normalize the vector, given its components as 2 of this. Let's take its first. What is this then? Cos theta. No, I just cannot debug this. I'm aware of perspective functions a little bit. Oh yeah, okay, but also, I think I'm just nowhere near as good at Desmos as you, so I don't even really know how the dot notation stuff works. Good, right. Good times. ASCII donuts, says Rice Cooker Man in chat. Good. Okay, right. Here's my plan for today. Not me learning to do a Rubik's Cube, although content right there. No, that's obviously the most frustrating live stream that anyone could possibly do would be trying to learn to do a Rubik's Cube by trial and error in a sim. Here's the simulated Rubik's Cube just fumbling for 2 hours. No, instead, I thought we'd do more fumbling around with prime numbers. Again, don't know what I'm doing, just going to try stuff, see what happens. Oh, it's not just multiplication. Oh, okay, and I've confused it for some sort of Python accessy thing. Always assume that it's tricky. That was dot for multiplication. G'day, right. Shout out to Ace Chewy 2007 and Tyloo somebody who followed while we weren't live, which is main time we get followers. I should spend more time not being live. And let's try and work in the direction of the Riemann hypothesis. That's a good motivation for the stream, isn't it? The direction of the Riemann hypothesis. Unfortunately, we're miles away. Last time we had some stuff going on with powers of numbers modulo a prime to work out. We were interested in the order and whether or not there was a generator. We had a theory that was wrong about the kind of symmetry that you might get for such generators. This was incorrect, and we worked out it was incorrect by trying to prove it, getting stuck writing ha on the board and then going and checking and exploring them. The good maths, like not correct, not true, but good process. And we now have the ha emote, which you can use. Murray and Maths2to2 in chat have already found the ha emote for when you are just not sure what's going on. We'll see how useful that is. This joins the pantheon of, there you go, Rice Cream Man. This joins the pantheon of wow, oh no, and ha. So if we ever have to go into emote only mode, have I got that? Yeah, I have an emote only mode, but we've now got several key emotions, I think, lined up. Plus RFL if anything ever goes correct. That's the suite. That's the suite of emotes. Do we need oh, just like oh instead of oh no, but just oh no, just the oh. It's kind of a bit ha. Yeah. Anyway, this was suspicious. Okay. So last time we looked through a proof that the units modulo p are a cyclic group under multiplication by finding a generator, finding something that's got the correct order. And we knew it had the correct order because it satisfied a particular polynomial. I'm thinking about these equations where you have something to a power as a kind of polynomial equation to solve. And we counted the roots, which relied quite heavily on the idea that polynomials modulo a prime have unique factorization. That we had to know what the polynomial was that we were talking about. I thought that would be something to explore, because the whole proof hinged on it. So I just want to sort of demonstrate what might go wrong. What am I doing? My home office is a complete mess today, so nothing's in the right places. There we go. I've got a pen now. There we go. So unique factorization means that you can't have the situation where two polynomials factorize differently. Sorry, one polynomial factorizes in two different ways. There is a classic counterexample to this that I'm always being shown that I keep forgetting. Let's try and work it out. So this is going to be a kind of example of not unique. Let's go non-unique because that's an actual kind of word. Example of non-unique factorization of polynomials in, I think it's polynomials over modulo 8. 8's not prime. In what's going to come up later on, I think that's important. 8's not prime. To prove it's not prime, we need to find a non-trivial factor. Well, we can do that because can think of several factors of the number 8, not just one and the number itself. Anyway, what am I doing? Right, I'm going to try and remember this. Now, possibly I should have tried to, set this up beforehand, but I think it works like this. Is it these factors? So these factors give you x squared minus 8x plus 7, but that's congruent to x squared plus 7, or x squared minus 1 mod 8, which is the same thing as x squared minus 1 actually, mod 8. Mod 8, for people who have seen this before, says that two things are considered equivalent or equal in some sense if they differ by a multiple of 8. So here this 8x, I'm imagining x is a whole number in everything that's going on today. Whole numbers only. Yeah, and it's going to be the same thing as, x take away 3, classic example, x take away 5, where this thing is also minus 8x, but then plus 15. But here's the thing, that 15 is the same thing as 7 in the mod 8 world, because 15 and 7 differ by 8. So you're allowed to switch out that 15 for a 7. Or even x squared, you can write this x squared minus 1. So this is two different ways of factorising. But it's not quite that. That's not quite what non-unique factorisation means. There's something else about how I have to say that I've factorised it into irreducible things. Two ways into irreducible things. So there's several other claims secretly going on here to make this actually an example of non-unique factorization. There's secretly a claim here that these are all irreducible elements, that they can't be essentially factored any further. Pretty sure that's what unique factorization means. Into irreducibles? Yes. You can't factor them any further. And there's also secretly behind the scenes here a kind of claim that all of these things are different. That this isn't just a different way of writing them, mod 8 or something, but none of these elements are secretly the same. I mean, of course not, because they will look pretty similar and they've got key differences, but there's kind of secretly a thing behind the scenes. Under the hood, what are we going to go? Are we going to mix metaphors? Yes, let's mix metaphors. Behind the scenes, under the hood, theatre and everything else all at once. So these are the same. Surprising. That doesn't happen with your kind of regular algebra that you learn in high school, where you factorise polynomials, and if you can factorise it into linear polynomials, then you're kind of done. Although I suppose, what do I think there? So you have this interesting thing. Let's think about factorization. In Rx. So for real polynomials, R is a field. So you get this kind of interesting thing that you sometimes have a choice about how you factorize. What do I want to do here? So something like, for 2x plus 3 multiplied by x minus 1 is the same thing. Oh no, I'm on a 4 in there actually, for the point that I'm making. You have this kind of thing that this is the same thing as x plus 2 times 2x minus 2, but that's not an example of non-unique factorization, really. I mean, in an everyday sense of the word, it kind of is, right? Here's two different factorizations of the same polynomial, right? They look different, these brackets are all different, but this isn't really what people mean by unique factorization, because both of these involve something where this is reducible, and so is this. Of course, you see what I'm doing, I'm just moving this factor of 2 around. So our definition of unique factorization, if we want to try and capture the way that Rx actually does have something unique going on, but Z8X doesn't have that kind of unique factorization going on, sort of genuinely different factorizations, and not just moving around a unit. Yeah, so I think I have to say up to units. Yeah, let's try and learn about unique factorization. I think that's my goal for today. I'm a little bit hazy on whether I'm supposed to put up to units here, or whether that's part of the definition of being irreducible. No, because units you can always kind of reduce something with units. Units are things that have inverses, because anything you like, you could write down x minus 3 multiplied by 3 multiplied by the inverse of 3 mod 8. 3 and 8 have both got inverses. Mod 8. Do I actually want, maybe I want the units here? Maybe I want units. Maybe I'm talking about the field, maybe not. No, because I want 0. No, forget that. No. Okay, good. I want 0 to exist. Otherwise I can't add stuff. And I would like to add. Yeah, I've got forget I said anything. This is general advice for the stream, really, isn't it? Forget I said anything. Okay, right, that's my plan. I think I would like to improve my understanding of what unique factorization is, and maybe I would like to get some more understanding of how it works for primes. So 8's not prime, but I think for primes you get unique factorization. Understand what unique factorization means for some polynomial ring in general. So polynomials where the coefficients come from some exotic number system like modular arithmetic or something. And I would like to understand why, if you have, in particular, integers modulo p a prime, you get unique factorization. That's right. That's an acronym. Let's write that out. So for this one in particular, has unique factorization. This was an important point in the proof that we were reading, relying on this idea that working mod P, you have unique factorization of your polynomials. There's no funny business going on where we wanted to say that you can see the roots of this polynomial, you can see the solutions. And I think this is something that's just in some lecture notes that I was looking at about a year ago. So partly, this is going to be a revision stream, I guess, because I think we've done this before. We're going to look back at something that we've streamed before. I found my lecture notes, or my lecture notes is pushing it. I found the lecture notes that I was using last time I was thinking about this. Oh, they are no longer on screen. Oh, I had this all set up and now it's broken. Is that going to come back if I do this? Do I have to accept it again? Okay, good. Learning. Oh, no, it's over here. Great. And it's the thing where if I resize it, then it doesn't. Okay. I found my lecture notes. Here we go. Bear with me. Okay, these we had on screen before, so the notes on here are from a different stream. Oh my goodness. Revision. So I now have the advantage of having my notes from on screen from last time I read this, including some other stuff. So I've picked this page from some notes on rings and modules, which is part of the Quintic quest. We're going to get really good at algebra to understand how we can't solve quintics. There is some stuff on screen here. This section is about, or chapter maybe, is about factorization in these two polynomial rings. But it's really Q that I'm interested in. This section is about, well, it's about being irreducible in Z, and ends up talking about integer coefficient polynomials. But I think we want to look at Q because Q is a field. We're interested, well, I'm interested today in ZP, so I want to think about the field. And there's stuff at UFD, where UFD stands for unique factorization domain. Yeah, great handwriting. I don't really mean. Don't know. Yeah. I don't think I've improved since last year. Look, this is perfectly easy to read, right? This says, and this is a note that I've scribbled last year, like fx, something that I'm interested in. But f a field, possibly, is a UFD because Euclidean domain implies, principal ideal domain implies unique factorization domain. I'm pretty sure that says field. It's a very short L. It might say fiend, or it might say fried, or it might say fixed. It could say field though, couldn't it? It's F. F is the first letter of field, and fixed and everything else that I've said. Good, right. These are polynomial. Look, again, just ignore the handwriting. That says polynomial rings, probably. That's the topic is rings, so there's a good chance it says rings. There's the R, there's an I. I don't need that. And then a little N that goes all the way over and looks more like an R than the R. This is how handwriting works. Good, right. It probably says field, which would be good because I would like to know about fields. This is kind of exactly the bit I would like to remind myself about. About a year ago, I wrote this note, excited, and clearly understood it at the time. Good. Why have I erased whatever's in front of this C? What was this? It was a Q. Yeah, goodness knows why. I don't think there's supposed to be a Q there. That's why I've crossed it out. Yeah, good. Okay. Yeah, let's carry on. There's a point here which says, we know from our earlier discussion that QX is a UFD. Let's prove this for Z. But that's the point of this section. I don't really care about Z. I'm going to try and look back and find out why all of this stuff is true and why this is what I want. But instead of the field Q, I'd like the field ZP. So that's my plan. ZP and Q are both fields because you can divide. You can buy anything non-zero. Everything's gone inverse. It's amazing. For Q, it's kind of obvious you turn the fraction upside down if it's non-zero. And for other ones in ZP, you use Bezier or something to find the inverse. It's great. Hello, Mean Machine Rex and Sensation Black 1984. Yeah, this is not good, is it? we're also jumping straight into some, what is this, page 39, halfway through some notes, and I'm now going to try and work backwards until I get to the bit which I think I don't understand. Forwards and backwards, that's how you read notes. Okay, so going backwards. And this is a bit where I think, so I need this, don't I? So I need, oh no, I remember this. This is also pretty bad, look. There's a proof here that's left to an exercise sheet, so I might have to try and find the exercise sheet. I need to do A-level maths, don't I, lol? Well, putting it off. I don't know. I think it's surprisingly, the stuff that we're doing here is surprisingly unrelated. Like, doing A-level maths doesn't really help in some sense, except for maybe it helps in some sense, but not very directly. Yeah, okay, there's complex numbers going on, but they're hardly doing anything, so. I mean, this says root minus 3 on the screen over here, but what's that actually doing for us? Anyway. Right, so I think I want to understand this. And look, there's a comment that says, don't remember why. So I was clearly struggling with this last time round. I might have bitten off too much. Ah, well, let's go. Goodness me. Okay, right. Yeah, this stuff is hard. Am I doing too much? Whoa, let's find out. Can I find anything about Q in here? Oh gosh, yeah, I also remember the notes at this point just being like, yeah, go and prove this. Go and do it on the exercise sheet. Which is very good for students, but I wouldn't mind if they just told me how to do things sometimes. Yeah, okay. Highest common factor is something like this. It seems sensible, but that's not the way around I care about, right? I care about the other way around. Is this something about the Euclidean domain going backwards? Yeah, okay. Right, so here's a definition of PID. So we don't need to go further back than this if we want to understand a PID. Every Euclidean domain is a PID. Yeah, so the argument here for something is something like generate the, so every ideal is principal. Good, oh, right, here we go again. Yeah, we got some Gaussian edges going on as well. Right, hang on. Okay, so let me see how much of this I can remember. So for these polynomials, you get a kind of Euclidean domain just by thinking about the degree of the polynomial, I think. You get a division algorithm, right? That says, yeah, so you need to be able to do something, don't you? To do the division, but more or less, some condition on your ring, but being a field is definitely great. If your coefficients are from a field, then I'm pretty confident that you can do a kind of division algorithm based on the degree of the polynomial. So start doing polynomial division. And I think the idea for this principal ideal domain thing is, on screen at the moment, is that you can generate the highest common factor in a way, using your Euclidean algorithm to generate the highest common factor of kind of everything in your ideal, which is but unlikely. Yeah, I agree. Maybe you do want a field. Luckily, I have a field. Is that strictly what I want? Maybe that's what I want. Yeah. Thanks, Megalomorph. I probably do want a field. I have a field. Yeah, with F a field over here is part of what they're going on about as well. This is what I've got underlined. It's the thing that I want. It's funny how I seem to care about the same things as I did last year. Oh yeah, polynomials was very much the theme of last time I was reading this sort of stuff, is because I cared about polynomials with coefficients in a field. Okay, so then I guess I don't really have a strong grasp on what an ideal is, but that's cheeky because that's the That's the whole point of these lecture notes, I think, is to get an impression of what an ideal is. Sort of, I don't know why they would have any finite set of generators on which I could run my Euclidean algorithm to find a PID, make a PID like that. I suppose. Yeah, hang on. What am I going to do? If you've got a massive ideal that includes loads of polynomials, like x plus 2, x plus 4, x plus 6, x plus 8, and so on, there's a massive ideal that contains all of those. How do I prove that one's principal ideal? What level maths is? Undergraduate, halfway through an undergraduate degree, maybe nearer the start than the end, depending on what sort of undergraduate degree you're doing. We're doing abstract algebra. Just trying to learn about. There's a bunch of definitions, and the definitions kind of fit together. The idea being that if you then want to say something about particular algebra, like working modulo P, you just remember some properties of mod P, and then kind of look it up on your list of like, it fits into these categories, so it's got these following properties, which is a kind of convenient abstraction way of thinking about lots of different sorts of algebra all at once. I think I just defined abstract algebra by saying it's like algebra but abstract. Sorry. we try. Yeah, megalomorph is gonna be very helpful in chat, I feel like, today. I'm just worried about. Here we got these two definitions on screen. I think Cambridge UK do this second year. Oxford UK do this in second year of undergraduate. Yeah, MIT apparently does second or third. Depends a bit where you are and what else you're doing. Right, can I back up a little bit? I think I want to get a bit more solid about why these things really are a principal ideal domain. Maybe there's a definition of principal ideal somewhere else over here. Maybe not. This is running a Euclidean algorithm, which is quite good, but you have this D function, right? For the you have some Euclidean norm thing. Anyway, never mind. Which works nicely for integers, but also works for polynomials over a field. Same way. Yeah, you've got to be able to divide the leading coefficients, so they should probably come from a field. Okay, right, good. Yes, this is the one I want. Here we go. Prop 127. Let R be a Euclidean domain. And pick an ideal in there, then it's principal. Perfect, great. And my vague proof so far in my head is take some finite set of generators, calculate the highest common factor, which is not really good enough. Right, okay, here we go. It's going to be constructive. It's going to say, go and look for the one with the least degree, or Euclidean norm, or whatever. Generated by a single element. How are we going to find that element? My plan was kind of to vaguely take the highest common factor of lots of stuff. Turns out no, just look for the one with minimal non-zero degree, which does make sense. Yeah, okay. Then the proof. Let's read the proof. If I is just 0, then you're done because come on, that's generated by 0. Otherwise, go and look for something with possibly a tie, minimal degree. Everything's got to be. Everything generated by that, you multiply by ring elements. It's an ideal, so you're fine. That's part of the ideal. Conversely, if you're in here, then now go and do the highest common factor thing. Or just run Euclidean algorithm one step. Yeah, with smaller. Yeah, and then this remainder would have to be in the ideal as well, because addition and multiplication and subtraction and stuff keeps you in the ideal. You're closed under lots of stuff. Oh, critically, X and Y are in the ideal. Q isn't, but that's how ideals work, so that's okay. And then R is 0 by minimality, so there you're good. Oh, that's okay, that's really good. So follow-up is corollary, or I say follow-up sometimes. Okay, good. My strategy of working backwards is pretty strong so far, because I managed to find a prop and proof for something that I didn't really understand. So, where am I at the moment? Trying to prove that ZP is a unique factorization domain. Currently understand that it's a principal ideal domain because of the argument on screen here that you just take the smallest element and everything else is multiples of that, the smallest being something about the degree. So you can take the smallest element and everything else has to be multiples of it, otherwise the remainders would be also in the ideal and smaller degree. This relies on the idea that you have this degree function and you can write stuff with this kind of remainder. Yep, let's just check the definition of a Euclidean domain really quickly, but I think I'm there. Here it is. Amidst the division algorithm. Okay, good. So what are the rules on this function d, called the norm, or I've been saying degree because I've been thinking about polynomials. Yep, there it is. Given a field f forms a Euclidean domain. Good. Oh, I forgot this one. For a and b, except for the 0 element, you can, whenever you multiply, you get a higher degree. Yeah, all right, okay. And given a and b, you can write it out like this with a decreasing degree. That's the bit I remembered. I didn't remember this thing. What's that doing? Huh? Okay. Quick aside. Ignore what's on screen at the moment. There's this thing called the Euclidean algorithm. It's really good. If you want to find the highest common factor of two numbers, like for 85 and 34, the division algorithm way to do this is to say, well, if you write 84 as some multiple of 34 plus a leftover bit, so here 2 times 34 is 68 plus the remainder would be 17. So anything that was a factor of 85 and 34 will also be a factor of your leftover bit. So you can now work on 34 and 17 instead. You can sort of reduce your problem so that instead of working on this large pair of numbers, you're now working on this smaller pair of numbers. And this sort of step of writing out a quotient and a remainder gives you a new problem with smaller numbers. And through all of that, you have to keep saying, you have to keep saying the word smaller. So you need, this works in general if you have some concept of smaller. So this definition on the board is trying to capture what's really important about the Euclidean algorithm. This idea that you're making smaller remainders. You can always write out quotients and remainders with smaller remainders. And then also some technical comment that I haven't really understood about the concept of smallness being nice on the multiplication, which seems fine. Yeah, so 17 is the remainder of dividing 85 by 34. Maybe I've picked a bad example because then 34 is a multiple of 17 and now I'm done. So the next step of the algorithm would be to write out 34 is 2 times 17 plus, oh my goodness, 0 remainder. And then you've realised that they're both multiples of 17. So therefore, they were both multiples of 17 being combined into one large multiple of 17. Aha, these things are both multiples of 17. Which is faster than factorising sometimes. Depends what the numbers are, depends how good you are at factorising. Good. Well, I have no idea. Probably not, right? My gut instinct is no. Something like... solutions in the Gaussian integers. Maybe I don't know. Maybe my answer should be I don't know. Can I set A and B to both be 1 and make it kind of a unit circle? And then I know the unit circle actually does go through some Gaussian integers, so maybe I should make C be the number 2 or something. And now I'm a bit suspicious. Although that still works because you can send it through 1, 1 or something. And X and Y can both be Gaussian integers. Okay, I'm going to go back to I don't know. Yeah. factoring is hard. Okay, so this is kind of abstract maths, right, where you take something that's been done for thousands of years and you try and take the key concepts of why does this work and generalize it. This is an attempt to talk about number systems in general, where you can get away with something like this. One that you maybe learn at school a little bit is polynomial division. So if you have something like some sort of polynomial, you can do polynomial division on that, where you'll write out a kind of quotient. If you're trying to divide it by x plus 2, you can write out a quotient and do this kind of polynomial division where you, oh my goodness, I'm making a mess of this, but you can do minus 2x squared. Why if I pick such horrible numbers and keep going to get a quotient plus some sort of remainder. And this is called the quotient theorem when you learn it in high school, I think. It tells you interesting things about what happens when you plug in minus 2 on both sides, because this term will die and this one will give you some number, which is the remainder. So there's some nice links between doing polynomial division versus evaluating the polynomial. Those are kind of quite similar concepts. Minus 8, minus 6, minus 14, so I think I have to write minus 12 on this side or something. The remainder turns out to be minus 12. God, I really wimped out of doing that last step. Let me just fix that. 2x squared minus 2x squared, because I don't want any, minus 4x. Oh, polynomial division, I used to be much faster at this, didn't I? Right, minus 4x, but I actually want plus 7 or something. And then minus 12, because I've currently got 14, but take off the 12. Good. Yeah, I agree. So the ideal, if you're, so in Z, if you have the ideal that includes A and B and everything else that's an integer multiple of those things, so this is kind of shorthand for any combination of like MA plus NB for M and N both in Z. That's what ideals do. They take any multiple of anything from the wider ring or number system and multiply over. And the result is that this is just the same thing as multiples of the highest common factor, which Meglemorph has put in chat. Does the factor theorem still work? Yeah, I think we've still got the factor theorem. I can never remember which way around the factor theorem is usually stated. Is it both? Am I safe? I'm going to look like a fool now. Factor theorem's on the map. I should definitely know what it says. Oh, hang on, one way around is obvious. This is the way you remember it. One way around is obvious. So it's something like if p of minus 2 is 0, then p of x is x plus 2 times some q of x. You can take out this factor of x plus 2. And which way around is it? This way is obvious. If you factorized it, then you can just plug in minus 2. And this way around is, like, interestingly, the factor theorem. Yeah, and then I suppose it's just going to be, if you have polynomial division, then you can just get on with it, I think, and sort of do the synthetic division, and you'll get the same thing. It'll all work out. It has to give you 0 remainder. Oh, but that's me using the fact that it's a Euclidean domain by trying to just do the division at all. Okay. I think Meglemorph, I think Math222 might be trying to work out the most general context in which you still have something that looks like the factor theorem. That's why they've said as long as we have no zero divisors. They might be thinking if you're an integral domain, if R is an integral domain, then is R of x, does that do some sort of factor theorem? And I'm no longer sure because, well, that might be too general because I'm not sure you can do any sort of polynomial division if you don't have a field around. I think you just get really stuck, can't you? If your leading coefficient isn't, if your leading coefficient is irreducible, what are you going to do? Like, you sort of multiply by a unit. What am I talking about? Okay. I'm really bad at these kind of converse questions where you can ask the kind of the opposite, which is what's the most general setting in which the following is true. I'm really bad at those. That's the abstraction question, I guess. For I would like unique factorization. What's the least I need to get away with that? How abstract can you go? Cool. Right. Okay. So Euclidean domain. I'm never going to remember that first bullet point with the star on it. But hey, the concept is that you can do division. That's going to be true for our ZP polynomials over modulo P, because you can do polynomial division and then the degree goes down. So you are ED. And then you are PID. And I think I now understand that because, and you're PID because, consider, so what have I got? Win for the first half an hour. And then this is going to be ZPX is ED, and then D of X is just deg X. ZP is field. That's all you need to make Euclidean algorithm go. And then so far we've seen that this is true as well. We reread the proof of that. Consider element with lowest non-zero norm or degree. And then what I'm going to need is PID implies UFT, and I think that one's really hard. Do I teach? Yeah. I'm supposed to be marking work. Maybe not now, but this evening. I do a little bit of teaching for one of the Oxford colleges. I have 5 students and I see them once a week. Oxford teaching is great. There's not a huge number of students really, and then they do quite a lot of this sort of small group teaching where I see Monday afternoon 5 students in 2 pairs and 1 singleton, and we talk about, at the moment I'm just seeing them for one of their courses, which is called Introductory Calculus, and they have 5 or 6 things going on at the moment, and they have 5 or 6 meetings a fortnight to go through them with either me or other tutors. It's good fun. But yeah, at the moment I've got the kind of easiest job where I just meet first year students on a Monday afternoon and talk about introductory calculus, which they're all fine at that. Somebody else is seeing them for courses that introduce more new material, let's say. Okay, back to the notes. So I think the challenge for the next, how long am I going to be live today? I don't know. I think the challenge is going to be, UFD stuff. Oh, hello. Look at this. Meglamorph's put loads of stuff in chat. Thanks, Meglamorph. Is this about Maths 2222's question about the factor theorem? I'm going to read it out. In any ring R, we can look at polynomials R of X, and we can always divide by X minus A. Ooh, even though we can't always divide by arbitrary polynomials to get Q of X plus R of X. How do we know this? Oh, if you're allowed a where R of X is a degree lower than X minus A, don't you need something to get? How are you going to get this bit? With an evaluation method plugging in XXA, we get the remainder. Yeah, I'm wondering about how are you going to write this QX plus RX thing in general. That makes me nervous. Yeah, it just works. What should I do then? So for monic polynomials, is it? If I look at monic polynomials, maybe that's the key. I'm fine because I get my x squared on the front, and then I get ax plus. I'm going to write 3 minus a here, and then all of these things are just part of your ring operation, so you're okay. Yeah, all right. I think I agree that works. These are all numbers that exist in my ring, including things like 3 minus a. So I can divide it by x minus a. Huh. I can imagine doing that with higher degree as well. Yeah, and then here's my remainder. So then I could do factor theorem stuff on that as well. And I haven't used any properties of the numbers except ring stuff about adding and subtracting. Okay, so you can do. So thanks to Meglamorph, I think we now understand that you can do something that looks like the factor theorem for monic polynomials with a leading coefficient 1 in any ring. It's pretty good. Yeah. Thank you. Nice. Good. Oh, I love this Twitch channel. It's got. Sometimes I wish that somebody else was, I could just be in chat. That'd be great. I don't know if I'd be as helpful as the people currently in chat. Maybe this is the right way around. Right, what are we doing? I was going to try and get back to that confusing page and then stare at it quite a lot. You have a unique HCF. Good. We shall see the PODs, UFDs. I would like to just get there. We shall need the equivalents of primes and irreducibles to actually show the PODs, UFDs. So you've got to eat your vegetables in some sense. So I think I've got to understand Prop 143, and then 144, and then 145. And there is a horrible bit there that is left for an exercise for the reader. Look, I can see it. This is left to sheet 2, exercise 5I. Ugh, lucky me. Right. That's 222 in chat. The polynomials with Z over Z8 is an example where there's no zero divisors, but you don't get unique factorization. Those polynomials you told me about, like x minus 3, x minus 5. Yeah, that was it. Megamorph's got it. Okay, cool. I'll just do my own thing over here. Okay, you're going to tell me the 4 times 2 is 0. Yeah, fair point. Fair play. This is like last week. Last week I struggled to prove something really simple about 2 different factors with no common factors. B divides A and C divides A, and I just struggled for like 5-10 minutes. And then after the stream, I did it straight away. It was great. Oh. Right. Okay, what are we doing? We're going to try and read the proof of Prop 143, then I might take a break for a cup of tea, then we might come back and struggle with 144 a little bit. Or maybe just read the proof of 145. Skip it. Okay, here we are. So part A, if you've got unique factorization, then your irreducible elements, those are the ones that can't be split into non-trivial factors, are prime, which means that prime in this world has this weird definition where prime means that if you divide a product, you divide one of the parts of the product or the other, or maybe both, which is a property that you've maybe seen about prime numbers. Here it is at the top. If you divide a product, then you divide one or the other. Property you've maybe seen for prime numbers. That's weird to use that as a definition of prime, perhaps, but that's what people do. Here we are. Okay. So the proof's going to work like this. We're going to say that x is irreducible. We're going to try and show it's prime, which means we need to suppose that divides a product. We then have that you can multiply it up to get this. The elements v, y, and z can each be factorized into irreducibles. Yeah, go for it. Unique factorization. By the uniqueness of the factorizations of this, it must be that x is present in the factorization up to a unit. Because it is irreducible and you have unique factorizations. This would be 2 different factorizations if we're not careful. Present in the factorization of y or z or both. Oh, that's okay then. That's what it means to divide y or z. Yeah, okay. Unique factorization has got this meaning where you might have the same terms in a different order, but we're okay. Okay. Chat's miles ahead of me. It's great. I sometimes glance over at chat and think, fun. Okay. Good. Right, other way around. Okay, so this kind of feels like my kind of intuition about unique factorization stuff, right? That you just sort of write out the factorizations and spot the terms. Oh yeah, I've been thinking about primes like this for maybe too much. That if you divide, this is the thing I was trying to prove. Maybe no, maybe not. If you divide a product, then you divide one bit or the other bit. That's the definition of a prime. So I wasn't trying to prove that, was I? I'm talking nonsense. G'day. Almost 3 o'clock. Okay, so part B, in a principal ideal domain. So the only property we've got now for part B is that your ideals are principal. You generate them with a single element. An irreducible element, one you can't split. If it divides a product, then oh my goodness. Oh my goodness. It divides one or the other. Right, okay, here we go. So say x is irreducible and that this is in some ideal. What is this? Irreducible element is prime. Okay. Why are you doing this? There's some ideal in between? What is going on here? Oh, do we not know if that's an ideal or not? No, that's weird. Of course it is. With the angle brackets, that means you take everything. It is y such that y is actually equal to I. What is going on? What is I? I think that just means ideal, but that's not ideal. So why isn't that I? Hello, John Oxland. What is 3 times the square root of 1,000? Square root of 1,000 is about 30, isn't it? It's about 90. Is it about 90? I think we're good. Or is that a cube root of 1,000, which is 10? Welcome to chat. Good to see you. Yeah, why isn't it? Okay, but am I being stupid? Why isn't this just... Why doesn't it just say that let's call that I as an ideal of R? Does the triangle not mean ideal? What am I doing? Yeah. Okay, suppose that, let's say it's a suppose that there's some ideal that contains this ideal generated by X in R, then, well, actually that one was also ideal. It was also principal, so it's generated by some Y, and so there's some Z such that is this. Or something. Or generated by some Y, so in fact you can generate X using some Y. Okay, so any ideal that contains this is principal like that. Okay, goodness me. By the irreducibility of X, what on earth are we doing? Irreducibility of X, we either have Y as a unit, and then I equals generated by Y equals R. What? If Y is a unit, then... Okay, if Y is a unit, then you're generating fine everything. I equals R. Or Z is a unit. And if Z's a unit, then X equals Y. Good, okay. Oh no. Hence X is maximal. Gosh, I've forgotten anything about maximal ideals. What are we doing? Oh no. Hence X is maximal. And so prime, hence X is a prime element, and absolute panic, right? That, oh no, this last sentence would like to use 2 or 3 facts from previous bits of the course. Oh, why are they doing it in terms of the ideals? Why are they doing some facts about ideals? The ideal is maximal, so the ideal is prime, so the element is prime. It just sounds so... Oh no. This feels like you could just do this the other way around, right? This has got to be easier to say. Oh my goodness. Look how many notes I've had to write over this last time I tried to understand this single sentence. Right, this is the next 6 minutes of my life, isn't it? This one sentence. What am I going to do here? I could go back and reread what a maximal ideal is, what a prime ideal is, and why being a maximal ideal means you're prime, and why being a prime ideal means that the element is prime. Or I could try and turn it all the way around. Because what I thought they were going to say is, say X is irreducible, is to say, suppose X divides YZ, because we're trying to prove that X is prime. An irreducible element is prime, so we're trying to prove it's prime. So now, consider, now I'd like to consider something like the ideal generated by Y. or something. Yeah, to try and steal this element of the proof on the screen. This is reducible. Not going well. Oh yeah, no, not this at all. Because the point of that was that x would be equal to yz. Oh no, maybe I have to understand what maximum ideal is. Maybe that's what it's come to. Right, okay, we're going to do that. My direct proof is not going anywhere. I don't know what I'm doing. Oh, that's annoying though. It feels like it should be a direct proof. Just using the fact that you've got principal ideals. So, goodness me. Yeah, so it would be something like you'd write down the ideal generated by these things both is generated by some element u. So then both of them are multiples of u. That's suspicious. So if x divides y, z, consider... Oh, have I won this back? If I had an idea that might actually... Have I had an idea? Original thought, maybe? Stay tuned. Okay, consider the ideal that's generated by both x and y is my cunning plan, because principal ideal, don't wow yet, we might not be there. Principal ideal means it's generated by a single element, which I'm going to call u, for some u. And now I'm on track, because now I can write that x would have to be u times v, and I guess also that I have y as u times w or something, but I care less about that. I'm suspicious about this, because x is irreducible. So one of these must be... by the irreducibility of x, I get to say either u is... Yeah, so then either u is a unit, in which case xy is the whole ring, which feels suspicious, but I'm not quite there. Yeah, so I got that it was the definition of maximal ideal, I think. I can't remember why you get from maximal to prime, or why you get from prime to a prime element. There's kind of two steps going on here. The and so here, and the add hence here, which terrified me, because it's kind of two steps using... I can't remember what's a prime ideal. I mean, I can kind of work it out, I think, but I'm trying to cheekily do this directly without remembering any of the terminology about ideals. It's an ambitious attempt. Okay, because if u is a unit, then this whole thing's a r. Or maybe x is equal to v, or v is a unit. Oh, if v is a unit, yeah, I'm sort of copying the proof a little bit as well, but if v is a unit, then generated by u is the same thing as generated by x. So then y would be generated by x, x would be a multiple of y. So in this case, where u is a unit, we generate the whole ideal. Yeah. Megalomorph remembers both definitions, and is... For Megalomorph, this is just a plain sentence that makes sense. Oh. Right, my direct proof is almost there, because if v is a unit, then I'm happy, because u is the same, generated by u is the same thing as generated by x, so y is generated by x, because that's what this was. This principal ideal is generated by x, which means y is generated by x. Nice. X divides y. And there's a thing over here. Oh, I've hit 3 o'clock and tea time. Cup of tea. I haven't quite got the idea for why if x is the whole ring, if you generate the whole ring off these two, x and y generates the whole ring, why that would mean that x divides z. Doesn't seem like it. Doesn't seem likely. I guess if I got some sort of combination of... I would have some combination of x and y that is a unit. So then I can make 1. So then, given that x divides yz, if I multiply both sides by z, I have this equation where x divides this thing clearly, x divides yz because there it is. So therefore x divides z. If you can make 1, you can do this kind of Bazoo lemma thing, where you say if you can make a unit, then you're good. I think that what follows. I think that works. Right, I think might be there. If you can make the ring, then in particular you can make the identity. And once you've made the identity, you can run this kind of mini argument to say, aha, I've now got enough facts, I think. Right, if that doesn't work, I don't really want to know. Maybe I should go and relearn what maximal and prime ideals are. Feels like they're important. Probably the proof halfway through there uses some similar ideas. If not, then I don't really want to know. Right, okay, I'm going to go make a cup of tea and come back. After the tea break, we're going to try and learn what on earth is going on with... I might try and find sheet 2 exercise 5i to get some idea. Maybe it's got some hints about Noetherian rings, which is named after Emmy Noether. And maybe we're just going to read this proof about unique factorization to work out why it's important that it's going to go PID on Noetherian and therefore UFD. Right, okay. I'll be back in a couple of minutes. I'm going to run an ad break and put something boring on the screen. See you in 2 minutes. You might like to use this time as well to grab a cup of tea. If you see an advert, then you're supporting charity. If you're out of the room making a cup of tea while an advert is playing, then you're also supporting charity. But if the advertisers are listening, they're all going to buy the wristwatches or whatever it is that you're showing them. Herb has already bought 5 cars off the back of Twitch ads, so keep supporting this financial model, donating to charity indirectly. Thanks, advertisers. Right, okay, bye. See you in a minute. I'm back. Hi, people in chat again. Yeah. Okay. Good. Right. Okay. Thanks for the tea break, Murray. Right. What? Yeah. Thank you. What's the worst that could happen? I've got tea now. I think the sequencing, so that I don't have to keep switching between stuff. I'm gonna have a read of this. I think I might have skipped it last time I looked. Hey. Thanks for the follow, Vector. Welcome to the show. We have a follow goal that you are helping with. The goal there is that we get to the interesting number 315, and then it's the smallest number without a Wikipedia page. I can't quite remember how that works. I think we celebrate by making a Wikipedia page. Let's see. Oh no. Yeah. Sorry to hear that, Megalomorph. I am reading along. Right, I'm going to read about principal ideal domains, and then I'm going to go and find this mystery sheet 2 exercise 5, which I actually remember last time I read this, just skipping it. The exclamation mark and the big line just means no, didn't do it. Oh, what's this cryptic note around here? Is this what prime ideals are? Is this the thing Megalomorph was telling me in chat? But I've got like this horrible hieroglyphic kind of mess. That's maybe me trying to understand it last time. Maybe it's an X, prime ideal. So A is an X. I swear the definition of a prime ideal is just the definition of a prime element, but you know, they're equivalent things, right? Or something? Oh, I don't know. That's sort of one extra step of applying a theorem, but never mind. If A, B, then either A is in I or B is in I. That's such a weird property though, right? That's such a weird property. Either A or B is in I. Oh man. I cannot get my head around that at all. Other than it's some sort of, abstract thing that you can write down, and then it might be the property that you need. But I feel like it's one step away from the thing about prime dividing AB, therefore prime divides A or prime divides B is kind of that rephrased, I think. Why is it called prime? Well, it's a bit like prime numbers, ideally. Ooh. The concept of a prime number has, well, in my understanding anyway, yeah, so the prime ideal stuff is related to prime elements. Maybe there's a question, why are those called prime elements? And it's really this thing about like, if you've got a product that's a multiple of 3, then either 3 divides A or 3 divides B, or both. You can say that for prime numbers like 3. This is not true if you replace the 3s with 8s, because 8 is today's non-prime of the day. Because if you put an 8 here, then these things might all know. There might be like 2 and 4 or something. That's your example of things that multiply. So the set of numbers which do this are the prime numbers. Counterexamples for composite numbers, you have this counterexample where you can write down the factors. Anyway, you can generalize that idea, which is then good because you can talk about prime numbers even in a world where you don't have factorization, unique factorization. Anyway, so you might have, it's a bit odd to me that, when you're a small child, we teach you this definition of prime numbers, and maybe we should teach you that thing about prime numbers are ones where if they divide a product, they divide one or the other of the terms. Maybe that's how we should teach you prime numbers from when you're very small, because that sense lets you talk about numbers more generally without having to think about unique factorization. I don't know, does our definition of primes kind of use unique factorization? I've said that, and now I'm not really sure that's true. Because what do you actually learn? You look at all of the factors of the number, and if it's just one and the number itself, that's a prime. Whereas in this course, at least, we're using the word irreducible for that concept, generalized a little bit to say, what if I've got more than one thing that behaves like one? Yeah. So these things are all related a bit. So in the sort of factors and multiples way that you can write things out in terms of whether it's a factor or in terms of whether the other thing is a multiple. And there's this word that's flying around on the screen here for an ideal. An ideal is supposed to be a collection of all of the, well, not just all of the multiples of the thing that's generating it, but inside the angle brackets, but kind of all of the combinations where you're allowed to add as well, and you're allowed to add kind of multiples of different things. So you're going to use these building blocks. What can you make? You can multiply by anything else, loads of multiples by any other thing, and you can add up these combinations. Because that represents this kind of idea that, well, it looks a bit like Bezout, I guess. Bezout's identity has, in a way, this idea that if you have A and B, and you might want to consider AM plus BN. That's when I'm saying Bezout, I mean the kind of chicken nuggets problem. The chicken McNuggets problem is this thing like you have boxes of chicken nuggets, and you have maybe a box of 4 and a box of 9, and you want to buy lots of chicken nuggets. And the kind of set of numbers that you can buy by only buying boxes of 4 or boxes of 9. You don't have to commit to buying at most 0 of each, and that's the ideal generated by 4 and 9 is an ideal of Z. There's this result that for whole numbers you can. Oh, do I mean that? Maybe I don't mean that. No, because I'm allowed negatives. Negatives. It's like a version of this where you're also allowed to sell chicken nuggets. McDonald's don't normally allow that. But here's a hack. If you go to McDonald's and say that you want to purchase 9 McNuggets, but also you want to sell 2 boxes of 4 McNuggets, then that's a way to purchase 1 McNugget. They hate that. It's like a sort of secret menu thing where you say, you're dealing with me now, take these 2 boxes. Refuse to elaborate. Sorry, that's not really the chicken nugget problem then, is it? Because the chicken nugget problem is that McDonald's do not accept nuggets. They only dispense nuggets. So you must use positive numbers or 0 only. Terrible stuff. Yeah. Just trade them, right? Just sure. If you want to leave with exactly 1 nugget, then, well, but see, let me tell you need some negative numbers in there. You got to get rid of some nuggets. Okay. So this ideal actually turns out to be all of Z. Sorry. It's not a good example, because once you've worked out this hack for gaining 1 McNugget, you can do that as many times as you like to get any number of McNuggets, or even spin the tables on them and thus get -3 McNuggets by doing it -3 times, or 3 times the other way round. This is a problem that I've seen on UKMT summer camps with, I think, coins in Fantasyland, where there's 2 sorts of coin. Anyway, the general notation for this is going to be that you generate an ideal like this. More serious example, if you're talking about polynomials, you can talk about polynomials that are generated by maybe 2 interesting different polynomials. So you might take a very basic polynomial like the polynomial 2 and the polynomial x, and this lets you generate, you can multiply. And the rules now are that you can multiply these by any polynomial you like and add them together. That's maybe more interesting because, well, yeah, you don't have negative degree, so you're kind of stuck with the constant coefficient being an even number, which is kind of interesting. Okay, other things exist. Rounding errors. Yeah, well, you don't allow negatives. Coin problem is a good thing. I've heard it called the stamp problem as well, I think. Let me just check those are the same thing. Maybe it is, maybe it's not. Yeah, I think it's the stamp problem. Chicken nugget problem, I think it's all the same thing. Good. Right, okay. Well, I'm pleased I did a chicken nugget example, and now I'm doing something else. What am I doing? I think I'm streaming Twitch while I try and learn about Noetherian rings. It's funny how that happens sometimes. Okay, here we go. I bet this uses some technology I've forgotten though. Okay, we're going to try and prove that you have unique factorization by imagining, if it's by imagining an element and trying to factorise it, I guess. If it's irreducible, then you are done. You have factorised it. Hooray! Can I reread the definition of UFD? Because I think it's into irreducibles, and I want to know that thing about whether you say up to units or not. An integral domain is said to be a unique factorisation domain if every non-zero non-unit element of X can be written like this, non-unit. Written like this. And then there's some terms and conditions on the next page where they are irreducible elements, and further, this factorisation is unique in the sense that if you do it in two different ways, into irreducible elements, then there's the same number of them, and possibly reordering them up to units. There you go. That's where I'm supposed to say up to units. Good. I haven't seen that movie. I should watch Office Space. Maths to do in chat is still trying to understand the string maximal ideal, prime, which I decided before the tea break that I wasn't going to engage with. So props for engaging with that. Maybe Megan Wolf will help you with the definitions of those three things. Right, what am I doing? Okay. I've checked UFD. Okay, if X is reducible, then you're done. You've factorised it. You've written it as just one irreducible. There it is on its own. Otherwise, reduce it somehow. Okay, but these things are not units. That's what irreducible means. Definitions. It's all definitions. It's very precise definitions being kind of glued together to deduce things from there until you get to say RFL. I've played this game before. If y is irreducible, then we're done. You have factorised it. Have you done that uniquely? I don't know where we're done at this stage. If they're irreducible, then we're done because we're just proving the existence that you can factorise into irreducibles. Otherwise, continue factorising. Right, let's say right next. Keep going. Right. If at any stage we lack any genuinely composite remaining factors, then we're done. If it doesn't terminate, crikey, okay, keep doing this forever, and you will produce an infinite, strictly increasing sequence of ideals. These are not equal to each other, so maybe cross out the equals bits of these. Strictly increasing? Yeah, strictly increasing. I think it's just, okay, subset, not equal. And each one, X is Y, Z. This is the correct way around, isn't it? Y is like a smaller number. It's a factor of X, so you get a larger ideal when you consider, for example, the multiples of 6 followed by the multiples of 3. And then I don't really have anywhere else to go because 3 is irreducible, but whatever. Okay, if you could keep it going through the alphabet, X, Y, A, B, C, then you're done. But, exclamation mark, I think. Principal ideal domains don't do that. This can't occur. Emmy Noether says no. This will terminate. So then you're done. You have factorised it. Now uniqueness. Okay, so uniqueness is the bit that I feel like might actually be more interesting. I don't know. It doesn't involve looking at quotient rings. Okay. Say we have this in two different ways, two factorizations. As P1 is irreducible, and so prime. Yes. This is the thing we were talking about before the break. Your irreducible elements are prime in a PID, which is the hard one, using the scribble in the margin or the thing that Megalomorphs talk about in chat. Stephen Wolfram streams, I didn't know that. Irreducibility, there you go. And so prime, P1 divides this stuff. Yes, if you do it with primes, it's great. Implies that, so then look, you've got these two potential factorizations, and you say, this P1 divides all of this. Dividing a product means you divide one of the terms if you're prime, and your irreducibles, which you've used for factorizing. A problem here with unique factorization is defined in terms of irreducibles, whereas the thing about dividing products is a thing called prime. Those are the, if you're irreducible, then you're prime in some contexts. Goodness me. Otherwise this, as Qi is irreducible, Pi is not a unit, Pi is this, like this. This seems reasonable. You're going to write it out. This bit here, this is already saying that P1U is equal to QI. That's what being a factor means. But then QI is irreducible, so this is pretty suspicious. One of those things has to be a unit, and it's not P1, so it must be U. And that's what we want. Good. By renumbering and incorporating the unit into one of the other factors, yeah, get rid of that. It's to assume that they're at the front by the cancellation law. Oh gosh, okay. So there we're using the fact that it's an integral domain. You haven't got any zero divisors. Okay, good. We have this. Proceed along similar lines again, ultimately showing that R equals S, and the two factorizations are essentially the same. Seems pretty good. Once you know they're primes, so proving that your irreducibles are prime is pretty solid, because once your irreducibles are prime, you can do this, dividing the right-hand side trick, which is then essentially enough to say up to units, you're done. The rest of this is sort of checking. It's the idea that you use the fact that they're primes. Okay, they all look like numbers on the screen, but I realised from the start that the context is supposed to be that these are all polynomials. Like every P1, P2 thing is polynomials. The irreducible polynomial is quite an exciting concept, because we're talking a little bit about whether you can factor things over certain number systems. You know how you can solve quadratics in some sense. That context aside, I'm thinking about these. Right, I'm going to try and get it in my head with polynomials. I'm going to try reading it again, but imagining everything's a polynomial. That sounds stupid, doesn't it? Okay, so take your polynomial, non-zero polynomial. Oh, if it's irreducible, then you're done. If not, start factorising it. So I can see a shortcut, I think. Maybe I can get away with this. Start factorising it where these things are not units. Now, if I'm in a Euclidean domain, if I'm in a polynomial ring, then I think I should be using the Euclidean norm here. Now, it might be true in general that you can use this Noetherian fact, this looks very good, to say that this process will terminate. But I think I don't actually need that if I'm just looking at a polynomial ring, because I can maybe rely on the fact that the degree is decreasing. You can't keep factoring forever. So weaker proof, but good enough, I think. Oh gosh, sorry, I can really shake the camera if I do that. I've got my elbows on the table. Really weaker proof, but I think sufficient might be, instead of this Noetherian idea for PIDs in general, I'm in a more permissive setting where I've got a Euclidean domain, because I'm thinking about polynomial rings. That's the main thing I'm thinking about. So maybe I don't need the Noetherian fact, because I've got my degree. Let me think about this. So if these are polynomials, otherwise write this, where y and z are not units. Now the units in ZPX, the polynomial ring that I'm interested in, the units are the constant polynomials. I can't divide by anything else, but I can divide by all the constant polynomials, the non-zero ones. So a reducible element reduces into sort of non-trivial things which must have lower degree, using the fact that it's an integral domain. So the degree of this product here is greater than or equal than the degree of one of the things. That's the starred fact from the definition of Euclidean domain ages ago. Star A, d of AB is greater than or equal to d of A. Brill for all B. Never knew I would need that before the end of the stream. Here we are. Good. I can just use degree, I think. I don't need this Noetherian terminating sequence fact. I think I've avoided the hard bit. I think I've found a way to understand this with polynomials. Here we go. So Euclidean domain means you can't keep factoring. That doesn't sound true in general, does it? Degree of a product is always larger, strictly larger? For non-units, so I've got something better than a Euclidean domain, haven't I? I've got a Euclidean domain where I've got pretty strong control over this concept of degree, which is a little bit stronger. Okay, I think I'm going to rely on that. You can't keep factoring forever, so eventually you terminate. If you're composite, then factor and keep going. Yeah, okay. Maths 2 to 2, my guess is going to be that's a maximal fact, right? If B is larger than A but not equal, then B must be the whole thing. That sounds like a definition of. Sounds like if I have the definition of a maximal ideal around, but who knows? Well done for working out how to put subset but not equal to in chat, or something that these lecture notes don't quite have. Anyway, okay, right. I think I've got this process that will get down to. I don't even need to write them as ideals. I can just write them as factors, right? So keep factoring. Keep factoring. The degree is going down on the things on the end of the question, so eventually it will have to stop. And now you have factorized it. Okay, so existence of factorization for polynomials over a field is easy, because you just say either it's irreducible, in which case stop, or it's reducible, or reduce it, and then keep going. You'll have to terminate because of the degree. Okay, brill. This paragraph is much easier in the context of a polynomial ring over a field. Good. And then uniqueness, I do need this fact that in a PID, irreducible is prime, which I haven't quite understood, but maybe I'll go and put more effort into understanding that. Like, I've kind of almost got there, but not quite. Okay, so in PID, we put quite a lot of effort into this in PID, but not enough. Irreducible implies prime, and then not quite sure why, so I'm putting this face. But then, now what are we going to say here? We're going to say that so in ZPX, factorization exists, and then this is going to be a kind of Nike swoosh, just do it. Degree decreases. I think that works. And then the uniqueness is along the lines of. The uniqueness is going to be along the lines of this paragraph at the bottom of the page, which said something like irreducible prime divides other factorization, and that's basically enough to get you around up to units or something. You're kind of there. Just do it. The degree decreases as you start factoring. If you stop when you get to an irreducible, of course, but you keep going. That's fine on me. Thanks. Okay, so then it'll be UFD. That'd be good. But you're doing these irreducibles to be prime, so the only thing I need to fix. So I have this ED, and then ED implies PID. You pick the thing with the lowest degree. I'm going to write degree there, I think, to keep this in the kind of context. Oh no, D, the specific. Okay, general fact or specific use of the fact? Which one do I put in my notes? It's got very specific down here. This bit, okay, last bit. And I think I'm going to look at the stack exchange thing that Megalomorphs put in chat, just for a bit of variety, because Math 222 has just said that it's good. Oh my goodness, everything has disappeared. Where have I done? I've managed to switch off absolutely everything. Is it all gone? Where's it all gone? Oh, I think OBS crashed. No? Is OBS still going? Am I live? I have no idea. I've lost Twitch. Oh, there it is. It's behind this Rubik's Cube. I'm live. Nothing happened. Nothing happened. What are you talking about, James? Yep, still live. Cool. Cheers, guys. I thought everything crashed, but I think I might have just minimized all my windows. What's going on here? This user on Stack Overflow 13 years ago asks why maximal ideals are prime. And there's a proof that doesn't involve the quotient. Suppose A is not prime as an ideal, then there are AB, such that AB is in here, but they're not individually not. Let B be the ideal generated by A, but also consider putting in A as well. So B is X plus AR for X in anything you already had, plus you could add on some multiples of A if you wanted to. Clearly A is, ooh, right, okay, and then here you are. It's in B, B might be larger, and B can't be the same because you've added in the element A, which wasn't there before. And A was maximal, so now B is R. We're trying to prove that if A is maximal, then it's prime. So now you've got everything. Putting in A was enough now, right? If you had the product in there and then you track in A as well, well, okay, you were maximal, so now it's got to be a whole thing. Maximal means that there's no ideals between it and the whole thing. Hence, you can write the identity, and now, look, this is what I wanted to do. I wanted to write the identity. That was one of the lines I had on the page in the margin somewhere. For some X and A and R and R, good. You just need to add in some multiple of A. And then you can make B by multiplying by B. And this is going to be, this is in, don't tell me, BX is in BA, right. Is in BA. They're telling me that this is a multiple of A, I think. Because, right, if I use words like multiple. Yeah, X is in BA. Oh, no, not sure. No, not true, not true. X is multiple of A. Not quite, not quite. But BX is in B times A. BX is a multiple of X. Bar is a multiple of BAR is a multiple of AB. Oh, you're telling me they're both multiple of AB, right? Yeah, you want to tell me that B is in this thing. Contradiction. Good. We're trying to show that B is a multiple of, or B is in this. AB in. But not A. I'm just fiddling around with the setup, sorry. Where were we? Which way around was it? Right, okay. And they've learned the I've read that stupid theorem that says that if A is maximal ideal, then you get a field off the thing. Anyway, never mind. And we just need to be an integral domain or something, maybe, but hey. Yeah. X and AB are both in A by assumption. Yeah. I think we're good. Okay. Cute. So the key idea here is this idea, right? It's maximal. We'd like to show that it's prime. So there's all set up for what we've got and what we're about to investigate. And then the idea is to consider chucking in A. And then that makes a bigger idea. We'll use the fact it's maximal, it makes the whole thing, it makes one in particular, and then you multiply up and say, aha, you've made B. Only using things that were in the original thing, because X was, let me follow it backwards, X was in the original thing for some X, and A times R, well, R is in the ring, and then we multiplied it by B. That is amazing. Like it a lot. Good stuff. Hello, Red Black VA. Would this come up in an Oxford interview? Gosh, no. Oh my goodness. This is very hard. And uses loads and loads of definitions that I wouldn't expect someone to know for an Oxford interview. Well done for finding the stream, though. If you'd like to see some actual Oxford interview questions, I did a stream for work recently. So I work at Oxford. I do this stream for work where we talked about Oxford interview questions on Thursday. So if you find the Oxford Mathematics YouTube channel, you saw that one. Hooray! Good. This is my personal stream where I talk about stuff that I'm trying to learn. That is, it'd be mad for me to try and ask this at interview. I think. Goodness me. Maybe everyone's in the same playing field of being confused. Yeah. Sadly, I'm also in that same playing field of being confused. You have to spend quite a lot of time explaining what's going on, right? Good. Okay. Where are we going? Yeah, we advertised it. Hang on, let me Google something. Very good. Okay. We advertised the stream. It always feels wrong to advertise this stream on my work stream because, you know, it's not an abuse of using the work stream, but hey, cheeky shout out. Right, what are we doing? We've got about 20 minutes, and I would like, I think, to spend my 20 minutes here understanding this thing. We just read some stuff, but we just read something about maximal and prime ideals. Well, let's see if I can piece together that last bit then. Given how inspirational it was to see. Whoop, that's not quite worked. Down a bit, across a bit. There we go. Notes on screen again. Given how much everyone likes that Stack Overflow bit, let's go back to the notes. Let's try one more time to understand proof of Prop 143 using the stuff in here. I'm actually going to switch off all of the scribbling. Just for a second. There you go. There's the original. Underneath all of that, wash away all of the mad scribblings around the outside and you get some actual lecture notes. Okay. So it's part B, I think, in a principal ideal domain. Yeah. Yeah, it's worse than the sponges. The sponges were nice. That sponge is not going very well. It turns out they're huge and loads of work. I've done some. No progress. And I know I did a stream about a year ago talking about how here's the plan for the thing, and it's going to be a big hollowed out volcano, and there's going to be loads of mega sponge inside. It's like, well, no. Why was I talking about such incredible plans that I have no chance of following through on? Oh well. Okay, what are we doing? Yeah, okay, so we got in here. I still didn't quite get this. What's going on here? Right, okay. Suppose that I is somewhere in between. We're going to prove it's maximal and then use the thing you just saw from Stack Overflow to say that it's a prime ideal. Hence, let's move the mouse out of the way. Hence, X is a prime element. So I think we're now happy that... actually, lots of this now makes lots more sense because we're considering some I in between. We're trying to prove that this thing is maximal. So we consider some ideal in between. Maximal says that you're the biggest one, except for, of course, the whole ring. So consider some ideal in between. And then irreducibility perfectly gives you the fact that either Y is a unit and you get the whole ring, or Z is a unit and these things generate the same ideal. So there's a definition of maximal. And then the Stack Overflow post tells us to consider any product in there. Consider throwing in an extra, throwing in one of the factors. Would that make it larger? If so, you can only make everything because it's maximal. Suspicious means that the other element was in there because you've now made everything out of just A. Skipping the details of how that algebra actually works on the screen. So therefore, it's prime as a prime. It's a prime ideal. Last step, and sorry, Megalomorph, I'm going to butcher this, but I do want to understand it properly. If you're a prime ideal generated by a single element, it turns out you have to be a prime element. Why is that the case? Let me think. So, prime ideal means product has one or the other in there. Just turn it into a fact about factors, I think, is my way of understanding this, perhaps. So that the ideal generated by X is all the multiples of X. If P divides AB, if X divides some product AB, then AB is in the ideal. And because it's a prime ideal, that means that either A is in the ideal or B is in the ideal. Being in the ideal means that you're a multiple of X. So translating all of that back together, the link between being a prime ideal and being generated by a single prime element is just that those are the same definition said in different ways. Let's do it again. Prime ideal says that if there's a product in there, one of the terms of that product is in that ideal. Prime element means if X divides a product, then it divides one or the other. And the translation works via, instead of saying X divides A, you say A is in the ideal generated by X. And instead of saying AB is, instead of saying X divides AB, you say AB is in the ideal generated by X. And then precisely the thing you want, that you go from AB to either A or B, is precisely what it means to be a prime ideal. I think I'm getting there. I think I'm getting there. Explosive cloud, some people use to earn proofs by induction. Yeah, the square is sometimes called a tombstone, which is, I think it's RFL. I think we got there. I think we're kind of there. This maximal thing that Megalomorph linked to on Stack Overflow, I liked that way of understanding it, I think, but this just kind of cute idea about throwing another thing. Prime ideals and prime generated by a prime element is the same thing. So you've got a prime element, and then I'm good, because if your irreducibles are prime, then when we get down to unique factorization, we got primes dividing both sides. Oh. Some chance of understanding this in tune in late. Fun to see it. James not being asked every 30 seconds what people's math scores are if they have an interview. It was quite a chaotic stream on Thursday. It's an important stream to do. It was a shame that in order to just get on with interview questions and do the thing that people have tuned in for, and pressure, because that stream gets more viewers than I think any of the other streams I do over the course of the year. And people clicked on it, maybe haven't seen anything else, who want to see about interview questions. In order to talk about interview questions, I have to ignore everything about Matt in the chat. And it's called the Matt Live Stream. This is the show that I do for work. It's called the Matt Live Stream, and we have to have this episode where I kind of ignore everything about Matt to just sort of move on from Matt. But yeah, it does feel bad. I'm better at fewer people there, and I have more of a chance of answering people's questions and sort of helping. But it's also now at the point where the stream changes character quite a bit when after the Matt, I can't be helpful anymore for the Matt because it happened. Just about the customer service of kind of things being processed at the moment. But people's questions change from helping to kind of analysing. Anyway, that's my work. Work's going to be like work, isn't it? Good. Okay, I'm pretty happy now. I think we've got to an understanding of how irreducibles primes are different things, but in a PID you can get away with them both being the same. So, do I mean the same? Technically, we haven't proved that a prime element is irreducible. Feels true. Is that true? If your prime is irreducible? Yeah, hang on, this sounds true. Suppose you could reduce your prime into a product AB. Well, that's weird because now P is equal to AB. That means P divides AB. So P either divides A or divides B. It seems a bit incorrect, doesn't it? If P is, let's turn on the notes again. Layers on. So just to check that primes are irreducible, probably in general, if you can actually factorize it, then P divides AB. It's prime, so P divides A or P divides B. Either way, you can write. Wait, what am I doing? What am I doing? Oh well, P divides A or P divides B. I was hoping this would convince me that this was actually irreducible, and that hang on. Primes are always irreducible. Yeah, I'm getting there. So we'll log it's this one, and A is P times some number C, and then I should plug it back in, right? So now I have actually P is equal to P times A, so P times C times B. So these are both units. So in particular, B was a unit, and this was not actually an interesting factorization. Good, okay. I think I'm using the cancellation law here as well. I think it needs to be an integral domain, but honestly, if it's not an integral domain, what are you going to do? Okay, good, cool, okay. I think it might be quite a natural point to sort of wrap things up, actually. Primes are always irreducible. In a PID, irreducibles are primes, following through some sort of logic about how... Yeah. Following through some logic about where things are going. I was just thinking about not PIDs, trying to think of an example where primes and irreducibles are different, but I've went out of doing that. Okay, good. That was my mission for today. I think actually we may have some success here. Let's try and write up a little bit on this board. Irreducible implies prime, and it's something like consider x maximal, so prime. That's terrible handwriting. Let's have one more attempt and then wrap the stream. Consider x maximal ideal, so prime. And I mean prime ideal, but then prime. I said no, though. I said it wouldn't happen. I mean, who knows? I think I'll be quiet. Nothing's impossible. Good luck with your St John's interview. That sounds fun. Have you got the email about that? If that happened? Or I'm not saying that you have. If you don't know, then this isn't me saying, but I have inside information. You have? Okay. Good luck with the St John's interview. On Friday, coming up quite soon. Okay, week 9 interview. They gave you just about a week's notice, didn't they? Oh, gosh, yeah. Where is it now? We're going into week 8. Friday, week 8? No. No. Friday, week 9. You were told on Friday. There we go. Cool. Phew. Okay. Phew. I thought they'd given you like slightly less than a week's notice. They haven't told you when. Good. Okay. Right. We will find out. They should give you a week's notice of the timing. Really. Well, 24 hours. Okay. Oh, nothing's impossible. Fine. Okay. That's me thinking about interview questions again. Saying, can I promise that St John's won't ask about rings? I probably shouldn't promise that St John's won't ask about rings. They'd have to teach you about rings as well. Anyway, thanks for joining in. Good job, chat. Very good chat interaction today. Good rings knowledge. Good to catch up with everyone. I'm away next weekend. I think I'm here in 2 weekends. Goodness knows. It's getting quite close to Christmas, isn't it? What does that say? I'm possibly here in 2 weekends. We will find out. Check Twitch to see if I've, at the last moment, cancelled my scheduled stream or not. Anyway, good to see you around. Yeah, good. How do I end the stream? Herb told me this. I end the stream by saying, I'm ending the stream. Fine.